this course, we'll look into our first real-world program. It will be a token, and you'll build onto it in your first assignment. As you can see, I just moved in VS Code, and for the rest of this course, because it's a lot more practical, I'm gonna stay that way. So in this chapter, we'll see our first token program. So first, let's define what token is. A token is a digital asset that users can share on-chain, exchange with other users. And there are two types of tokens. There are the fungible and the non-fungible token. The fungible token are interchangeable, meaning that two tokens are exactly the same. So there are two approaches on Aleo for building those kind of tokens. The first one is by using a private state, and the other one is by using public state. So the reason there are those two approaches is that they both have inconvenience and advantages, and we'll see about that in this module. So let's jump in by creating a creating a new Leo program. So we'll just use the Leo new command, and we'll just call it token. So this will create a new directory, and we'll move into it. And as you can see now, we have our placeholder transition main, and we'll just remove that. And here we go. So our token program has a token.aleo program ID for now. We'll change that later for deploying, because on-chain there must exist already a token.aleo program ID. So let's start. So what is the public approach for building a token? This is really your usual approach as you would have on Ethereum. And the idea is that we just define a mapping which represents the balance of each of our users in this token. And it associates an address to a balance, which we can define just as a U64, an unsigned integer. Okay, so every user has a balance, and first we'll define a function in order to actually mint our tokens. So to do so, because we'll update mapping, we'll create an async transition, and we'll just call it mint. Okay, so this transition will take a receiver, because it will be public on-chain. It is an address, so we just define it as a public input, and we'll take an amount as well, which is a U64, which is the amount that will be minted. So it's a async transition, so it must return a future. And here we go, we have our functions. Okay, so it will just return the finalize for our function, which is just a call to a public function. So it just returns the future to that call to that finalize function. And we'll pass all the arguments we had before to that async function. So now let's define our async function that will be executed on chain, and it will take as an argument our receiver, an amount from above. We don't need to state those as public, because obviously all async functions have public inputs. Okay, so now that we have our base, we can see how the function executed on chain actually works. So the way it works is that it will just read the old balance from the user, and it will add to that public balance the actual amount we passed as an input. Okay, so let's read the old user balance, which is a U64. And this is just reading the contents of the mapping, but we'll not just use the of the mapping as a key of the receiver, but we don't want this function to fail if the user actually has zero balance. So what we'll do is we'll provide a default value, and so we need to use a get or use function from our mapping to actually for this line to actually not fail when we call it, and the user the mapping balance on the user receiver is actually not defined. Okay, and so now what we'll do is we'll define our new balance, and typo here, and our new balance will be a U64 as well, which is just the old balance, and we'll add to that the amount that we are minting. So the minting function will create the token, give it to the user, and then we need to update the mapping. So we'll use the set function from mapping, and we'll just at the receiver key set the new balance here. Okay, we're good. So now we have our first mint function. Actually, we don't want everybody to be able to call that main function, so we'll add an admin address. This will be a constant in our program that only that will define an address. So we just created a Aleo account for all our tests, and we'll just copy our address as the admin. And now we're good. We have our admin address here, and we'll just verify that the color of this function, so self.color, is equal to the admin. So that way we're sure that only this address can mint tokens. Okay, so we have our public mint function. Now we have our mint function, we will actually want users to be able to transfer tokens. So we'll write a function from that, transition for this, which will be the transfer transition. And it will take a public receiver address as an input, and a public amount. Actually, I got it here. Okay, and it will return a future, because all the modifications, the updates of the balances will be on-chain. Okay, and same way here, we'll actually just return the future to an on-chain call, async function call. Okay, so here our async function will be finalized transfer, and it will take one more input, which is the color of the function. So we are sure we're transferring from the color to the receiver a certain amount. So here it is the sender of the transfer, which is an address. Then we have our receiver, which is an address as well, and an amount, which is an unsigned 64 bits integer. Okay, so what does it do is that it will update two balances. The first one is it will update our receiver balance. So it will just read the balance first, then it will create a receiver new amount, new balance, and this receiver new balance will be updated by adding the amount that is sent, and then we'll just set it. So the balance of the receiver will be set to the new amount. Okay. Here, same way as before, we're using the get or use function to be sure this doesn't fail. And we'll actually do the exact same thing for the sender, but instead, so we'll update for sender error here. But instead of actually adding to the balance, what we will do is we'll remove from the balance. Okay, and here we have the sender as well. Okay, we've updated it everywhere. Okay, so now we have our public transfer function. And actually, it will always fail if the new sender balance is below 0, because this will not be a U64, and so it will not be possible to actually execute that function. The problem with that approach is that it has two issues. The first issue is that it is mostly on-chain. So the main function is mostly on-chain, the transfer function is mostly on-chain, and it does not leverage at all the property of Aleo that it is possible to execute the code actually off-chain and prove that execution off-chain. So it's really more expensive to actually use a function like this that updates public state because you gotta synchronize all the update state of the public state updates. So actually it does not leverage Aleo at all. The second problem with this approach is that obviously it's all public. So anyone can track on-chain by just looking at the transactions, what were the amounts that were sent, what the receiver's address for those transactions are, so and the sender as well. So everything is public. So now let's copy that code and actually, to keep it for later, but actually update it in order to see how we can have a private, more Aleo-like approach to this problem. Okay, so let's first define a record, and that record will define our token. So our token has an owner, which is an address as any record, and it has an amount, which is just a U64. And so now that we have this record, when you own it on chain, it means that you own some token. If you own two of those, it means that you own the sum of the amount of those two. So how do we actually write a main function? This time we don't have to write an async transition because there will be no on-chain update. And it will simply be return. It will have the exact same inputs as before, which is the receiver as an address and the amount as a U64. And it will not return a future this time, but it will return a token record. Okay, so now that we have our function defined, we can simply create a new token, which will be the token that is received, that is minted and received by the user. And it's simply defined like this as a new record. And we'll have our owner, which is simply the receiver, and our amount, which is the amount provided as an input. Okay, and then we can just return that token. But here we don't want, same as before, we don't want everyone to be able to mint, so we'll just add an admin address and check that the color is equal, so assert equal, the color to our admin. Okay, and also we actually need to define the admin address somewhere here. And let's just copy the address we have here. Okay, so now we'll need to add a transfer function. And the way our transfer function will work, it will simply take one of those records as an input, which is the in token, let's call it, which is token, and it will return an out token. And because we define this as a token input, we will have that token consumed when we call that transition automatically, no need to do nothing extra, and we'll return a token, let's call that out token, and return it. So actually the receiver of that token will need to provide that as an argument and an amount as well. Let's copy those values. All of those values are private because private is default for input variables in Aleo. So I don't need to add the private tag, although I could to be more explicit. And the owner of that out token will be the receiver, and the the amount is that. So here the problem with just doing that for our transfer function is that if I have a record in which, or a token record in which I have, let's say, 10 tokens and I would just want to send 5, it will actually consume all my 10 tokens to send 5 of them. So how can I actually receive my change for the tokens I created, for the token I transferred? I will actually add another token here, which will be just my change. Okay, so the change token will just be a token record as well. And this token record will have our former token amount as an amount minus the amount that was sent. So here you can see that the sum of the token transferred plus the token, the change token, will be the amount that we had as an input in our token. Okay, so it's just that the receiver right here is not the receiver of the transfer, but it's the owner of the token that was spent here, or the signer of the function. That's the same. I could have used self.signer because we are sure that the signer is the one that transfers. Okay, so we also need to return both of those tokens here. And here we go. We have our private transfer. So this approach is very, very useful because it's very cheap to create transactions with it. But the problem with that is that on Aleo, program cannot own records. And so if you want to lock in a program some records for creating rules, to a program some tokens for creating rules for that program to be able to spend them, you cannot do that using private transfers. So you would want to use a public transfer for that. But the problem is we still want to be able to have those features with our private tokens. So the way we do that is that every token defined on Aleo will actually include both of those approaches at the same time. So let's now jump in how a real Aleo token would work, which is with a hybrid approach. So let's just redefine all the functions we had here. Our mint function will stay the same, but the name will change to mint private. And so here we'll include our former mint public function, and we'll actually just change the name for mint public. And that way we have both of those solutions. If we want to mint to a program address, we can just provide that program address to the mint public function. Of course, it will be executed on-chain and create that balance for that program on-chain. So we call that the public balance of an address. And if we want to mint private token, we can do that for just the users because an address associated with a program cannot own records. We'll use that mint private function and it will create a record for that user. So obviously users can also have a public balance, and the programs can just have a public balance, no private balance. Okay, so those transfers function we defined earlier, here it's our transfer private function. Same here as before. It just works for transferring from and to accounts of users and not actually programs. And the former transfer we had in our public approach, we'll just call that transfer public. And here we go. Now we have our transfer private, transfer public, all of that. But what if we actually want to have a user own some token privately and send it to a program as public? So we will need to add extra functions that convert token from being private to being public. And so very rationally, we'll just call that our transfer public to private function. So let's start with that. So transfer public to private will be an async transition because it will need to actually update the public state. It will have a receiver and an amount. And because it's from public to private, the output will be a private token. Let me just rearrange that. And it will be a record, which is a token here. So it will also include a future here because it's an async transition. And actually, sorry, the future is always the last output of a program. So I put it as the last output. So the token will be received by the receiver here, and the amount is simply the amount sent. There is no change because it's the origin of the transfer is public. And we'll also make a call to our transfer public to private future finalize function, which will return a future. So actually, I will update the name because it will be too long. And I will call finalize public to private. Okay, we're good. And once I have done that call, I will simply return both of those values. First, our token, which is not a change token, but a token, and that future for that on-chain call. So the finalize function will be defined right after, which is a function, an async function here. So what are the arguments? Well, we'll need to update the receiver, the sender balance. The receiver balance will be updated by just sending that new token as private. And so the sender is self.color, and we'll need to update it with that amount. And so here we have the sender as an address input, and we have the amount as a U64. Okay, so now we'll just update the balance with just removing the amount from the sender balance. So here we have our old balance, we read it exactly as before, we remove the balance exactly as we did here, and we'll just set the new balance. Okay, so here we have our new okay, so here we have our full function. Okay, so now let's do the exact opposite. We'll have a transition for transferring a token from private to public. So what this function will have is a few arguments. The first one will be the token that is consumed because it's from private to public. So it will be a record token, the in token. And we'll have as well receiver, which will be public. So sorry, here the receiver was private actually, and here the amount is public because we'll need to send it to the on-chain part of the transition. So here we have a public receiver because the receiver here is public, and we'll have a public amount. And we'll return, so we'll have a public update on chain, so we'll return a future. And the thing is, because there is an input token, we'll need to actually have change on that record. So we'll create that change as an input and as an output, and we'll return both those values. So here is the change amount. It's simply we remove from the amount, the old amount that was in the token. We remove the amount here, and then we'll create a new record and we'll return that here. We'll also return a future, and the future is just a call to the public state update here. And so it will send to the on-chain function, the receiver, the amount, so it can do those updates on the balance of the receiver. And let's just add that update here. So that update will just read the balance of the receiver at the new amount, at the amount to get the new balance, and it will update that mapping. And here we go, we have our both approach. And so what we can do now is use a pattern that we have a lot on Aleo, which is we can create a record, for instance, privately to a user, and we can have a program where so users can send those records privately between each other. And at some point, they can call a program where they store their token, for instance, for staking or for DeFi, for sending, for spending, for exchanging it, or for anything really. And actually, that program will own publicly the token because it cannot own the actual records to get it privately. And the user remains private because he sent from private to public. And that way we're sure that his balance remains private, as you can see here, because this is a record input. The address of the owner is encrypted. So now in next chapter, we'll see how to deploy that program on chain. Okay, so the first step to deploy that program will be to change its ID, because as I said earlier, the ID most likely already exists on the chain, and it will have an extra cost to use a program ID that is shorter than 10 characters. So we'll update that ID. There are two places where we need to update it. The first is at the top of our program right here in the Aleo source file. So let's just rename it token zLearn, simple token zLearn. And the second place where we need to update it is in our program.json. So now if we run Aleo build, see it builds, and we have our build output here. And we can actually deploy it. So first, we'll need to update the env variable with the one we have in our Aleo wallets. And you will need to provide testnet credits in order to deploy your programs. So make sure you have set your Aleo wallets in testnet beta network for testing. And you can go look for your private key right here. So don't share that private key if it's not your wallet on testnet. And you need to provide an endpoint, which is the endpoint for an Aleo client, and the network you're working with. Okay, so now that we have set all our environment variables, we can actually deploy our program by simply using the Aleo deploy function. Okay, so as you can see here, it provides me all the costs for actually doing that deployment. And so it then asks me if I want to actually submit the transaction. So I will just click on Y for yes. And now we have our deployment transaction that is on chain, broadcasted to the broadcast endpoint of the Aleo client that was provided here. And now our deployment transaction should actually be on chain. So in order to check that, we'll go on testnet.aleoscan.io. This is the explorer we'll be using in this course, which was made by Haruka. It's a very good explorer. You get all the information you need for developing. And as you can see, the transaction is accepted. We have the transaction ID here, the block, and the deployed program ID. And if I click on that deployed program ID, I can see my program on chain, the source code, which is the Aleo instructions that we had here, and in the build folder. And now we have our program on chain. So if we want to actually execute function from that program, let's say we want to mint some token, keep in mind that you will be only able to call the mint function if you have that address. let's just use Leo, execute, mint privates. The receiver will be myself. I provide my address, and the amount will be 100 U64 tokens. So actually here we have created that execution, but we have not broadcasted it on chain. So if you want to actually deploy that on chain, you will need to add the broadcasts argument, and you will also need to add the program argument with your program ID here. And this will create the execution and send it on chain. It will ask for a confirmation as well, and here we are. So we have our transaction ID that is here, and we can put it in our Explorer, and it's unconfirmed yet. You can see the total field for the transaction. Because it's a private mint, it's really cheap to actually mint, and as you will see, when we mint publicly, it will be a lot more expensive. So if we call the public mint function while it's in progress, so let's reload the page. Okay, our transaction was actually accepted. And so as you can see, we can see all the transitions that were executed. So the only transition we created, we called was mint private. And you can go look for that transition execution. So you have the inputs. As you can see, the first input is private, the second one as well. And you can see the outputs. Same here, there is a record that is encrypted. And actually, if I connect my wallet to the website, as we can see in our program right here, we have a new call that is a mint private function. We'll make a mint public, confirm our mint public call here, and it should appear in the ledger. So as you can see, we have very simple programs right now with just one transition. But when we see later, we'll be able to call external programs in the composability module. And so you'll be able to see all the transitions that were called by your program. So the time to finality on Aleo is supposed to be about 5 seconds or so. So it will really depend on the amount of validator on the network, and this should improve a lot with time. So here we have our transition that was just accepted. As you can see, our total fee here is a lot higher than what we had before, and this is one of the reason why we prefer to use private records, private states on the ledger instead of using public mappings. So now let's move on our first assignment. So now that we're in the more practical part of the course, we'll have some assignment to make sure you actually get familiar with the Leo programming language, because the best way to learn is actually to build. So we're gonna have an assignment about that simple token program we just saw earlier. And the idea is to get familiar with that program by just updating the function, its functions. So the idea is that you will add a tax mechanism to that program. So every time a transfer is done, the admin address will receive some percentage of that transfer. So you will need to update the 4 transfer transitions for that: transfer private, transfer public, transfer private to public, and transfer public to private. And you will, for the transfer private function, you will add to the private balance of the admin a certain quantity of tokens. The idea is that you will have a new constant variable up here, which will define the tax amount. It will be just a U16. It is defined as the per 10,000 units of the amount that is sent. So let's say we have one here, it's one base point, we call that. Then the amount that is taxed will be the amount sent, multiplied by 1 over 10,000, and actually it will be the floor of that. This is in pseudocode, in order to get 0.01% of the total amount. So each base point, each U16 here is 0.01%. If we have 10 here, we would have 0.1%. Okay, and so in your code, you will just implement that calculation. Make sure the admin receive that, and the sender actually send must. And the receiver receives the amount minus that. So in the transfer private function, this amount would be sent to the admin as private in order to not disclose the amount. In the transfer public function, it would be added to the public balance of the admin. In the transfer private to public, it will be to the public balance as well. And for the private to public, it would be to the public balance as well. And the reason for that is that for those three functions, the amount is a public variable. So it would not make sense to hide that amount from the users. So now it's your turn to work. You now know how to write simple programs as tokens. In next module, we'll explore more complex patterns to build real-world applications.